Hello. I wanted to take a look at translating sine and cosine functions from section, I do believe this is 6.4, indeed it is. So translating the graphs of sine and cosine, I just kind of want to discuss a small piece conceptually that you guys are going to encounter when or you all will encounter when you're dealing with these trigonometric functions or graphing these. All right, and I kind of want to underline a bit of this. All right, so here we have what is called the argument. All right, so these functions are translated. I mean, everything I'll say this, everything you learn from 171 about functions applies here. All right, and that deals with vertical translation as well as horizontal translation. All right, so for that, we are going to take a blast to the past and revisit something from 171 that helps us here, and that's dealing with translating functions horizontally. Oh, well, I made it disappear instead of having it join our screen. So I'm going to mush our notes real quick, and we're going to focus here on the book. All right, and you can find this on page 268. This is going to be in section, I believe this is 2.7. It is. Section 2.7 in the book, or page 268 in the book, gives us an example of horizontal translation. All right, so if we take a look here, and I'll grab my cursor really quickly for you all. Okay, so we're going to define a function g by setting g of x equal to f of x minus c, where c is a real number. All right, what this does here is anytime we are, adding or subtracting a constant inside the argument, we're going to see a translation, a shift horizontally. Okay, so and it is counterintuitive. All right, so the way you got to think about this is you should always try and write your horizontal translation, right? Your arguments here as the independent variable x minus some constant, okay? And if this constant is if your constant is positive, all right, what I mean is if you write x minus and you put a constant in there and your constant's positive, it will read x minus 3 or x minus 5. If your constant is negative, right? So let's say you had negative 3 or negative 5, it will read x plus 3 or x plus 5 initially until you rewrite it. And when you rewrite it, you're going to have x minus parentheses negative 3. That's going to help you with the idea or the fact that this is counterintuitive, all right? So when you see subtraction in the argument, it's actually shifting to the right. And when you see addition in the argument, it's shifting to the left. So by us kind of focusing on this c and always writing x minus or independent variable minus whatever our constant is, it allows us to see that constant is either positive or negative. All right, so let's go back to what we have in 172, and that's dealing with the shifting of trigonometric functions. All right, so the same things that we talked about with making a table will still apply here. All right, so our b in this case, b is equal to 1, which implies that omega, or the period of our function, is going to be equal to 2 pi. All right, this is the period of this function. So we want to break the period of our function up into 4 equal parts. That's what I said in that last video, all right? So our change of x would be equal to the period divided by 4. In this case, it's going to be 2 pi divided by 4, or pi over 2. All right, so every pi over 2 units we move along the x-axis, we will see the graph of the trigonometric function either rise from 0 to 1, to rise from -1 to 0, or it will fall from 1 to 0, from 0 to -1. All right. So what I like to do is I like to go ahead and get my everything written out. All right, and then I like to go ahead and add my shifts in. Now, there's a couple ways we can do it. So we have to know that originally this function starts off at 0, which is why I like to sort of write my, let's see, my x as, and this is not equal, this is actually a colon. So my x is as 0. Now I'm adding pi over 2 to each of these recursively to get the tick marks in which my graph will be graphed along over that one period, right? But now we're seeing some shifting here of pi over 4, right? If I can spell shifting, right? So we have some shifting of pi over 4, and this shifting, because this is x plus something, is going to be to the left, because if we rewrote it, we would rewrite it like this. And that will help us see that there is actually going to be shifting to the left here. All right, so it's going to be shifting back to the left, so we can modify this by subtracting pi over 4 from each of these, all right? And this is where just being handy with fractions is useful, so you might as well just accept, all right? So this is going to be negative pi over 4. This one's going to end up being pi over 4. We have 4 pi over 4, which is going to be equal to 3 pi over 4. We have 6 pi over 4, which is going to be 5 pi over 4. And then we have 8 pi over 4, which is going to end up being 7 pi over 4. All right. So those are all of our x. This is our new x's, right? This is the ones we want to graph along. So these are our new x's for the table. And again, that trick that I taught you about where cosine or sine starts will still apply here. You can just use just a tiny unit circle, and it should work out for you. So let me get me a little Cartesian plane here, and then move it over. So we're here. Now, we want to determine where we start, right? So the ordered pair is going to be 1, 0 here. Remember, cosine is x-based, sine is y-based, so cosine starts off with 1. But since we have an amplitude of 3, cosine will actually start off at 3 this time. So it will go 3, 0, negative 3, 0, and positive 3. Enjoy.